Hi, everyone. Welcome to the sixth edition of the Data Scientist DataDays. I'm really happy to be here and to introduce our fantastic guests and fantastic jury members today. Just really quickly to bring back the DataDays in their scope. The idea is that here at Data Scientist, our alumni are completing fantastic either data analysis or data science projects, and we want to showcase some of these projects and show them to you. That way, you can get an idea of what type of project you can expect, but also get a taste of their work, their methodology, and their fantastic ideas behind all these fantastic projects. Now, to quickly put these projects back into perspective and today's uh, timeline, we'll start off with a really quick introduction of our three jury members that are here with us today to challenge and even critique, I guess, these projects. And then we'll start with a bit more thorough introduction of each of these jury members. But this thorough analysis of our jury members will be done throughout the DataDays. So we'll start off with Alban, and then we'll move on to the other jury members that I don't want to spoil for you who they are just yet. Um, but it will be quite interesting, and then we'll also have these two fantastic projects that we'll showcase with the original creators behind them, and as I mentioned, all the fantastic work that they've done. So without any further ado, let me add on our three jury members, which will be Alban from Data Scientist, Francois, who is an alumni and fantastic today freelance data scientist, as well as Mark, who's our external jury member here to introduce them. So Alban, as I mentioned, he's a professor here at Data Scientist. He's part of the MLOps teams. And he's actually the lead MLOps here at Data Scientist. Mark is the founder and CEO of a company called Scorpio, which he'll be giving us more insights into in just a couple minutes. And then, as I mentioned, Francois, an alumni of our courses, who's today a fantastic freelance data scientist that you can call upon if you ever need some external aid. All right, so let me start off with a quick Q&A with just Alban. Alban, hi, how are you?
Hi, Theo. Hi, everyone. I'm fine, thank you.
Thank you very much for taking the time for being part of this jury today. Maybe just a few questions just to introduce you to our fantastic live members. Well, can you give us a bit more insights into what brought you here?
Oh,
What drove you to become a professor here, data scientist, and what are your day-to-day activities?
yeah. So, first of all, as data scientist in the member of the professors, we have all many roles to play. Like we are going to do master classes, we're going to participate in the project, and we are going to create new lessons every day. So we have a lot of roles to play, and one of the roles that I like the most is to be what we call mentor of projects. So during our training, we always insist on the fact that the trainers are going to participate in a project, but they often need someone to guide them because at the beginning they are not very um, well trained to create something from nothing. And so this is the task probably that I like the most. And for example, I was the mentor of the project AeroBot that we will see together today, which was one of the projects that I like the most. And I just to give you some insight, I actually mentor many projects in a lot of different trainings, and it's always very interesting for me to uh, try to see and challenge them to look at different aspects of data science.
Fantastic. As I mentioned, you're the head of the MLOps department here, data scientist. What kind of brought you into the field of MLOps, and how would you define MLOps in maybe just a couple words?
Yeah, so MLOps is a very new like a mode, like the evolution, some kind of the um, work of a data scientist. Um, Actually, I was not at all trained to do MLOps during my schools and my first training, but I wanted to discover this subject, and this is something I was able to do during my job at data centers, because we are always able to train ourselves on new subjects. And so this new formation that we are doing now for a few months is going to be, I believe, in the future, one of the main training in data scientists, as well as data analysts and data scientists, which is something that is a lot of asked by companies nowadays, and is going to be part of the data science environment. So what is MLOps concretely? It's like someone who is able to train a model, but also to deploy this model in a production environment. And so this is a skill that is now mostly done by the data engineers, but can in some ways be done solely by the MLOps, which is going to be part of the whole life cycle of the data science project, from the training to the deployment.
Fantastic. And just maybe to gloat a little, because it's always necessary, how many projects would you say you've mentored here at Data Scientist in these past few years?
I didn't count them, but it probably can count them in 100 probably, because I'm here for a few years now, and projects are launching every week probably. But every project I've mentored was a bit special in a way, because I when I'm trying to help people to do something, I always want them to have their own way of thinking, to maybe add their own paste to the project I'm mentoring. So what is the most important for me is that I'm letting people explain the same with the project inside the project.
Fantastic. Thank you very much, Alban. We'll get
Thank
back
you,
to you
Theo.
and the other jury members at the end of the first presentation. And now I think, without any further ado, let's start with the first project, bravely named Unhappy Earth, or maybe Unhappy Earth. I don't know exactly how to pronounce that. I'll add their presentations. I'll let them do the talking. And thank you very much. And please welcome Nicholas and Olga on this project.
Hello.
Hello, everyone.
And welcome to our Unhappy Earth project. We're very happy to be here. And after a few slides, we will demonstrate our Streamlit app. It contains a large part of text, but you will be able to come back to it anytime, thanks to the link we will give to you. The question of global warming has become a major subject, and yet it is still debated at the very time when its manifestations and consequences are more flagrant every day. Here is a simple definition. Global warming is a global phenomenon of climate transformation characterized by a general increase in average temperatures, notably linked to human activities releasing quantities of greenhouse gases, and which permanently modifies meteorological balances and ecosystems. Also, global warming is incredibly costly at all levels, humanly, socially, geopolitically, financially, and economically, according to a United Nations report published in April 2022. Therefore, anticipating and better understanding its consequences are becoming a priority for many companies and organizations. Our objective is to make available to a curious and non-specialist public, using reliable and fully accessible data, an analysis of global warming. We will answer the following research questions using the skills we acquired during our training at data scientists. Do the available data confirm the phenomenon of climate change? Is warming actually observable in time and space? How does it appear? The tools of data analysis and data viz let us acquire, explore, clean, merge, visualize, and analyze our data. What degree of correlation exists between the emissions of carbon dioxide and the evolution of temperatures? Statistical tests, linear and polynomial regressions evaluated by a performance metric allow us to establish and analyze these degrees of correlation. And finally, what are our temperature predictions for the next few decades? Thanks to machine learning, we will build a predictive model of temperature evolutions. And next, we're going to show a Streamlit application. Olga is starting by presenting our data sources.
So first of all, we are going to talk about the data sets that we used for our research. We identified two main data sources. One of them is Berkeley Earth, and the second is Our World in Data. If you are interested more in these sources, you can find a little bit more information in our presentation. But we will go straight to the data sets. From the first source, Berkeley Earth, we used the raw information and we transformed it into three data sets for our research. The first one is global world temperatures. The second, it's temperatures by hemispheres. And the third one is temperature by countries. All these files, they have a similar format. We can see a short example just over here. At the beginning, there is a short description of the data set. Then we pass to the reference table. In our case, the reference table corresponds to the average monthly absolute temperature for the period starting from 1951 till 1980. We will see just in a few minutes why we need this reference table. And thereafter, we pass to the main data set, which is composed of a space-separated table of 12 columns. First four columns give us the information about the year, month, monthly anomaly, and monthly uncertainty. The last 8 columns, we didn't use them in our project, so we just delete them, and we are not going to talk about them here. To explain more precisely what are anomaly and uncertainty are. So anomaly, it's the difference, positive or negative, between the real absolute temperature and the corresponding average reference temperature. To make it clear, for example, if this February of this year, 2023, it will be established that the average world temperature is about 0 degrees. And our reference table, it's we can see that the value it's 3.2. So in that case, the anomaly in the second month would be minus 3.2 degrees Celsius. So it's just the difference. So it's quite easy to understand, I think. Then the uncertainty. The uncertainty is some kind of margin of error of the temperature in one moment of time. So using all this raw information, we transformed it into 3 data sets, and as I told just before, and we can see the examples of the data sets that we obtained. The first one is global temperature, where we recalculated the absolute temperature and the moving average based on absolute temperature. The second data set, it's temperature by hemispheres, where we also recalculated the absolute temperature and its moving average. And the last one, it's temperature by country, where we have absolute temperature by country. This last data set, we used it to construct a graph. So here we can see temperature, the evolution of temperature by country we want. We can tap in the bar the country we want to see, for example, Spain, and it will appear in our graph for further analysis. From the second source, Our World in Data, we obtained the information corresponding to carbon dioxide emissions. The raw data were also treated, and we obtained 2 data sets. The first one, it's global world emissions divided between land use emissions and fossil fuel and industry emissions. And the second data set, it's carbon dioxide emissions separated by country. Similar as with global temperature by country with carbon dioxide emissions, we could construct a graph. I would like to notice that here in this graph we can observe the worldwide emissions line, so we can use it for comparison with any country. And also we have a bar where we can tap the country we search, for example, Russia, and also it will appear in our graph for further analysis. The second data set corresponding to carbon dioxide, we can also represent it on a graph, but we have just two lines. The first one corresponds to fossil fuel and industry emissions, and the second one to land use emissions. And as it often happens with raw data, we found that there were missing values. So we analyzed and we saw that in global temperatures data set and temperatures by country, there were not so much missing values. So we used a linear interpolation to replace them. But for data sets by country and corresponding to carbon dioxide emissions, there are quite a lot of missing values. We saw and we understood that these missing values comes mainly on the periods where the country couldn't collect the information due to, for example, to geopolitical instability or like war, for example. So we let these missing values as they are. And as you could already understand, some files like by country or by hemisphere, they were coming in separate files, so we put them together to obtain just one. And finally, we had these 5 data sets that we used for our further research. And now we pass to confirmation.
Can we confirm the phenomenon? To answer this first question, we present a graph from the global land dataset showing the evolution of global monthly temperatures from 1750 to 2021. We chose to display the rolling annual average, making the general trend more visible. We can observe, despite local variation, a growing trend. Since the 1850s, the visible average has risen between 1.5 and 2 degrees Celsius. Up to the half of the graph, around the year 1880, the temperature variability and the uncertainty are much greater. The data collected at this time are less reliable because of the sensors used and the limited number of meteorological stations. This uncertainty and its correlation to the fluctuations during the first decades is clearly represented on the graph. Establishing precisely the beginning of global warming is a subject of disagreement between experts. While most research correlates it with the Western Industrial Revolution, other studies indicate an early onset. Global warming is very gradual and undergoes cyclical variations that make accurate dating difficult. Nevertheless, by studying the graph again, we can observe a much more explicit, strong and continuous trend from the mid-1970s. In the previous decades, the global average temperature even seemed to be quite stable, which caused strong controversies at the time. From the data frame, we also calculate a 1.94 degrees increase since 1850 and 1.63 degrees Celsius since 1900. So yes, global warming is a reality. Let's now visualize the evolution of temperature in different parts of the world, starting with northern and southern hemispheres. In order to obtain a smoother curve and more readable measurements, we calculate again a rolling average over 10 years. As for global temperatures, we cannot precisely identify a starting point. Both hemispheres show an increasing trend, but their behavior is different. In the south, the rise is gradual and constant, while significant variation appears in the north. Over the 5 last decades, from 16.9 to 18 degrees Celsius, i.e. 1.1 degrees in the south, from 10 to 11.8 degrees Celsius, i.e. 1.8 degrees in the north. It makes it difficult to confirm where the warming started first, but we can observe a faster warming in the northern hemisphere. In order to validate this interpretation, let's focus on a different scale. In the following graph, we can define 2 groups of countries displayed with different line styles. This allows us to visualize and identify similar evolutions by region, in our case, by hemisphere. We find on this graph the previously observed elements. Warming is faster in the northern hemisphere, solid lines, than in the southern hemisphere, dotted lines. On all the selected countries, we can even observe that the further north the countries are located, the more the temperature difference is visible. Let's visualize the evolution of temperatures in all the countries where the data could be collected. The following graph allows you to navigate through time from the first measurements, 1743, to the most recent, 2020. Missing data are displayed in gray, and the color scale does not vary to allow better comparison. The increase is visible. Almost all countries took on at least one darker hue in 2014. To identify the temperature increase in all countries, we take the temperatures observed at the beginning of the previous century, 1900, as a reference and compare them to the temperatures observed on a chosen year. We land again on our previous observation. The rise in temperature is on average higher in the northern hemisphere and increases globally as you go north. However, this is not uniform. Knowing that climatology is a complex science, both local and systemic parameters should be considered. So next is the evolution of temperatures correlated to carbon dioxide emissions. Here, we will analyze and model the relationship between temperatures and carbon dioxide emissions from a data frame reduced to the period 1860-2020, of which we display an overview here. We compare the evolution on the 4 main variables on the next graph. The rise in temperature seems to follow that of total CO2 emissions, carbon dioxide. We note a drop in these over 2020 linked to the overall drop in activity during the COVID crisis, but unfortunately, it will have no impact on the climate. We now determine the correlation coefficients between our variables using the Pearson statistical tests. On the heat map, we visually identify the degrees of correlation between each variable of our data frame. We can already note an almost perfect correlation between emissions from fossil fuels and industry and total emissions. This widget allows us to select 2 variables in order to submit them to the Pearson test. We can see here and total emissions are strongly correlated. Here and land use emissions are only mediumly correlated. It does not increase a lot years after years. Fossil fuel and industry emissions and total emissions are very strongly correlated, as we saw that, because fossil fuel and industry emissions represent the largest part of the total emissions. And now temperatures and total emissions are again strongly correlated. And it is this couple of variables that particularly interest us. We model the relationship using regressions. We start with a scatter plot. These 2 variables are strongly correlated. We observe a certain linearity in this graph. The objective of a linear regression is to explain one variable by means of another. With a polynomial regression, the relationship between the explanatory variable and the explained variable is modeled by an n-degree polynomial, which we do thanks to the linear regression and polynomial features function from scikit-learn. Note that a 1-degree polynomial regression is a simple linear regression. As you can see, the higher the degree of regression, the more its curve sticks to the scatter plot. We evaluate the regressions with an R2 score for each degree. Scores increase with degrees from around 0.92 to almost 0.97, with a serious risk of overfitting for the 4 and 5 degrees. Therefore, we can say the model is efficient and confirms that carbon dioxide emissions are indeed a major explanatory variable for the rise in temperatures. Though let's be careful, despite these very satisfactory results, we must keep in mind that in this context of statistical study, correlation or linearity do not necessarily mean causality. And now let's hear Gergen about our predictions.
So now we will talk about the forecast and if can we predict the temperature over the upcoming years. To answer this question, we looked in internet several existing models to predict time series, and we choose Facebook Prophet because it's quite simple to use and it perfectly fits to our objective. So as any forecast model, we need to train our data. So for this purpose, we didn't use the whole data set, but just the period when the absolute temperature is increasing constant and explicit. We saw that this period corresponds to the years between 1975 and 2022. In this period, 1975, the average temperature was about 8.7 degrees Celsius, and it passed to 10 degrees Celsius in the year 2022. That corresponds to a 1.3 degrees Celsius increase, which is quite huge for the planet. So once the model trained, Facebook Prophet gives us the forecast, and we can represent it also on a graph here over. So the forecast starts from the year 2022, and we can see on it that the temperature over the next 50 years will continue, will follow an increasing temperature evolution. For more detail, we can decompose this forecast into two components, the trend and the seasonal deviation from the trend, but we will focus here just on the trend. So we can see, as I just talked, the temperature on the year 2022, it's 10 degrees Celsius. And with the prediction, the temperature in 2072 is expected to be 11.9 degrees Celsius. And we are talking about an increase of 1.9 degrees Celsius increase over the next 50 years. So it's really, really huge increase for our planet. So our forecast is based on the premise that the temperature will follow the same trend as the past years without major climate action. And we also compared our research with existing studies, and we saw that our results are quite fair and reasonable, but far from optimistic. Yeah, so that's why we use the name Unhappy Earth for our project. And now we pass to the conclusion. Of course, our objective was not to discover America, but just to test the knowledge that we acquired during data analytics. But we could reply to the questions that we had at the beginning of our project. So we can say that we can confirm and quantify the global warming. We can say that carbon dioxide emissions have a strong influence on the temperature increase. And we saw a 2 degrees Celsius increase of temperature for the next 50 years, according to our forecast model. So we were limited on time, but otherwise we could complete our research, adding other causes and consequences, like, for example, greenhouse emissions, like methane, evolution of the distribution between natural soils and soils exploited by and for human activity, global sea and ocean level rise, and the frequency and intensity increase of disaster. As we think it also has a strong correlation with temperature, as we can see, unfortunately, on the news this last time. So we arrived at the end of our presentation. Thank you for your attention. And if you have any questions, you are welcome.
Thank you very much, Nicholas and Olga. Let me now welcome also our jury members so that they may ask a few questions that they've been holding back this time.
Yes, thank you very much, Nicola. Thank you, Olga, for this presentation. I learned a lot of things. It was interesting. I have a few questions for you. First of all, you said that there is a strong correlation between the emission of carbon dioxide and temperature of the Earth, but you also said that this correlation doesn't doesn't mean that there is a causality. This is not enough. What could you say to someone that is, let's say, climato-skeptic and that deny the fact that there is a link between those two variables?
Okay, I would say to that person to take a look again on the graphs that we showed in our presentation, because if the temperature would follow a normal increase, a natural increase, it would follow the same trend more or less as before. But we can see a very sharp trend deviation from that I would from the trend existing before the Industrial Revolution. And especially in the Northern Hemisphere, after Industrial Revolution, we see that the temperature started to increase much more faster as before. So this explains that the humans put their acts now to this global warming.
Okay, thank you very much. I may have another question for you.
Yeah.
So we saw that you used mainly two models. One to try to see the trend between the correlation between carbon dioxide emission and temperature, and the other one was to predict the temperature in the next month, next years. So this was two very different models. The question was, do you think that which one of the two was the most difficult to implement, and the reason why it was more difficult?
Yeah, me, I did that one of the forecast. Nicola did that one of the carbon dioxide. I think they were not extremely complicated, because you need just to put the components and it calculates the result. But I would like to say that during this project, the most difficult part was to use GeoPandas to show the evolution of the temperature on the maps. So it's our third team member, Boris, who did that part, and we saw it's quite complicated to do.
Okay, great. Thank you very much. I'm now let Francois ask if he has any question.
Yeah, first of all, great work. It's very impressive, nicely done. My two questions are related. You know, if you measured the impact of emission, did you also consider some ways that this impact can be mediated, can be stopped, or lowered with respect to your projections? Because, for example, water vapor, which is a consequence of global warming because ice is melting and etc., and there's more sunlight coming into contact with the water surfaces and generating more vapor. For example, this has been shown to progressively stop um, sun rays from bouncing off the earth because it's covering up the earth, these water vapors, for example. Other factors could have contributed to diminishing the rate at which you computed your projections. So did you consider any kind of slowing down, or did you come across any kind of slowing down factors that could make a more happy Earth?
Well, actually, maybe with more time we could have got a different approach. Actually, our model of regression, whatever its degree, will not have provided significant results with, for example, absolutely no emission starting next year. Probably a model based on cumulative emissions, so measuring the total quantity added year after years in the atmosphere, would have been more appropriate to answer this question. And again, maybe with more time, and we wish we could cross our research with ocean rise level data, because the more the surface of water, it obviously have an impact of how the sun reflects and the vapor created and etc. So it could have been very, very interesting, but it would have been a slightly different approach, and unfortunately we didn't have time for this. But this could be very, very interesting.
Thank you. Can I ask one more question really quickly? How confident are you into the number that you produce, saying that this will rise by 2 degrees in 50 years? Because, as you know, it's very complex to measure temperature on the Earth. First of all, it's a question of altitude. It's a question of where you are, and etc. And atmospheric pressure comes into play, and the instruments in the past weren't as accurate as today. And can we really add all these temperatures together when some of them are written, to the decimal, and some of them are not to the decimal, and yet we're producing a number saying 1.5 or saying 1.7? How confident are you with, and did you measure any kind of uncertainty about your measurements?
If I may. So actually, we are quite confident regarding the temperature that we measure, especially on this last 60 years, because the models that are used and the fact that they use anomalies instead of absolute temperatures, the models and the fact that there are a lot more sensors and so on. So we know quite well what the temperature is, and there are a lot of bias that have already been taken into account for that. On the other hand, the models that we use for the prediction are very, very complex. And even nowadays, the scientists from the most advanced research labs cannot predict what is happening right now. We are still surprised when there are big floods and fires and the melting of the Antarctic and so on. So these are quite still a surprise to us. So the models are really complex, and they involve things like El Nino and
Volcanoes.
so many things. So we are quite confident regarding the real temperature that we measure, but we are not that confident regarding the prevision, of course.
Thank you.
All right, I'll ask a few questions as well if I have still time. Well, first of all, thank you for this. I think it's a very nice thing to say to climaters, skeptical people, look at numbers, look at very simple numbers, simple things, analysis, like not simple data collection and data processing, but simple averages over the world, over the years. So that, first of all, thank you about that. I have two questions I'd like to ask. The first one is about at some point you're showing what are the field emissions. You're showing the industry emissions and the field emissions, and we see that the field emissions over time are not so much increasing. We've been told a lot. It's a well-known thing that meat is responsible of a lot of emissions. Meat consumption is rising and contributing to CO2 emissions. I was wondering how can you explain this flat curve of the field emissions that we saw earlier.
Sure. Land use emissions is a very complex notion. So if I can clarify it just a little bit, depending on how the soil is used or not used, carbon dioxide and other greenhouse gases can be released in the atmosphere, like with mass agriculture, and livestock, like meat production. In its chain of production, it produces a lot of carbon dioxide, and the animal themselves release a lot of methane, which is another greenhouse gases. So this carbon dioxide can be released in the atmosphere, or it can be absorbed and stored in the soil with photosynthesis, decomposition, and soil respiration. So the annual production of land use, the annual land use emissions are not growing, but still, even if the number are quite stable, it still means that globally we have not been able to reach a balance between in the way we use and affect the lands. And said like for the past few years or decades, there have been a lot of deforestation on one hand, but on the other hand, there have been many strategical plans for replanting trees, for making forest and forest exploitation more sustainable. So I think we have not this growing trend, but still, if we had the right balance, it would be zero. And obviously, it's still not. But we need to put much effort in order to tend to this balance between soil emissions and consumption, absorption by the soil.
Thank you. I have a small question, maybe if I have time. So now let's forget about skeptical people for a while. Let's try to use all the knowledge we know about greenhouse effect and everything. How would you feature engineer your prediction model? Like if you have some more time for the project, could you tell us what you would like to try to make the prediction more accurate using all we know about greenhouse effects, such as like you talked about methane. There is also the fact you talk about the fact that the cumulated CO2 matters more than the emissions. So yeah, if you had to start on this topic, how would you handle it?
So I will reply to this question. Yes, of course. In our project, we used Facebook Profit, and we used just one component. It's the average temperature evolution in the past years. So we used the historical data set to predict the future. To obtain something more precise, something more detailed, of course, we need to add other components like carbon dioxide. But we were limited on time, so we didn't do it. So the answer is to add new components. We can see a good prediction in the Berkeley Earth website already based on the evolution of the carbon dioxide emissions in the future. So I don't know which model they used. I don't think that Facebook Profit can give that results, but it's like we are beginners in this topic, so I can't say exactly which name of the model it's possible to use, but for sure it's possible.
And if I can add something more than the model, we will need to build a team with like geologists and biologists and really climate experts and cross their knowledge with our skills to build a really good research work and a very complete research work. It's crossing many fields actually. That's why this question, this issue globally is very complex.
All right, perfect. Thank you very much, everyone, for this project, both to the project members, Boris, Nicolas, and Olga, but also to the juries for their first round of intervention regarding this project. We now have a few minutes to meet a second of our jury members, which is Mark. Mark, hi. Thank you very much for accepting our invites. Maybe if you could give us a few minutes. So I did do a little teasing at the beginning of who you were and what brought you here, but maybe if you could give us a bit more details into your presence here, but also Scorpio.
Yes, thank you, Theo. I'm an engineer, data scientist, machine learning engineer. I worked a bit at Tesla, Oakin, Another Brain, and for like 3 years now, I've been I founded and ran this research and development agency that is Scorpio. So we are helping companies to externalize their machine learning needs if they want to, and give them resources and setup to get started with such projects, such use of the data. Lately, we have decided to start machine learning as a service approach, trying to kind of externalize the MLOps as well in a way. Like all the client have to do now is just ask a question to an API and use the result, use the answer. That's the only thing they have to do, and that's the way we chose to handle the MLOps issues on our side and simplify life of clients, because this MLOps field is huge. And lately as well, 3-4 months ago, we started a podcast that is called Data Driven 101, where we try to interview and have a conversation in depth with people working in the data sector, in the data field. Those people can work on any kind of subject, any kind of like position. That what is interesting is to see how people are using data in different ways, with different tools, in different situations. So we've interviewed people from like huge groups like L'Oréal, from startups that have been successful, like overseas. We've interviewed people. Like the next episode is from the data scientist of the French rugby team, where he's telling us about how using data for sports. So very different topics, very different things, and it's been a very interesting conversation for me as the interviewer, and it's been a lot of fun talking with all those people. So yeah, that's all I can say about me.
Thank you. No, it's really, really interesting. I think my next question is regarding some of the kind of news in the data science and AI world, and having your intake into the Chat GPT vs maybe Bard debate that's going on. What type of use cases are you seeing there? Do you see this revolutionizing the world of AI, but also in the day-to-day activities that a data scientist might do, or an ML engineer, etc.? What are your kind of intakes? I know this is like a whole topic on its own, but maybe in a few minutes,
Yeah.
what would you have to say about that?
Yeah, a few things I can say out of top of my mind. So one interesting thing is that ChatGPT is a revolution based on the UX more than the rest. Like GPT-3 existed before, did almost the same thing that ChatGPT. So the first thing I'd like to mention is that what made ChatGPT had so many users in so little time is really the user experience that changed from something where you had to begin writing something and GPT-3 would complete what you started writing. Now ChatGPT is a chat, and that changed everything for most people, and including the more technical people, and that's something we have to keep in mind. On the use cases part, well, I cannot tell what the future is about, but I think what is very impressive with those tools is the capacity of synthesizing things, taking a huge data set, which is internet, and building like summaries of things. For instance, like tourism, what can I do in this weekend in that city? What are things that are that I like? Like you see my past activities. What can I do in this city for me? We can imagine any kind of usage. Obviously, I think on the e-commerce side, like seeing what is the best product for me, or on the seller side, what are people thinking of my product? Those are things people are willing to pay for today. So I think that ChatGPT could help them to do it more efficiently. There are many use cases we can imagine. I think the main problem we have today with ChatGPT is the fact that he invents a lot the answer. Like we cannot really use it for saying like, take this text and make a summary. Right now, he's really using knowledge based on what he saw on the internet, and so technically there is some work to make it trustworthy, and I mean, to make it as powerful as it seems, like to make it really useful for being efficient at work, being efficient at our job, making it a productivity tool. I think he needs to be trustworthy, which he isn't right now. That's the main thing. I think on the side, like Bard versus ChatGPT, I haven't looked Bard closely yet. I think things are moving very fast. But more generally, what I would say is that I would bet that what happened in the image generation side 6 months to 1 year ago would probably happen in the NLP side as well. So what we saw with the images is OpenAI taking lead with DALL-E 2, making generation of images very powerful, and using a public data set that is Lion, 5 billion images. This is not a private thing they used. People try to build something on it, and Stable Diffusion was an open source version of what DALL-E 2 was before. And a few months after OpenAI, there was an open source alternative. So I think text NLP is known to be more difficult. But I still think that the data set used by OpenAI is a public data set because it's the internet, and we will probably at some point see open source versions that are efficient, and can be at the same level as ChatGPT.
Thank you very much, Mark. Very happy to have you among our guests, and I think you did a fantastic transition between this interview and the next project because you mentioned the word NLP. So I think from there, and I just want to do once again a little bit of teasing. I want to give it off to Hélène and Ioannis, who will be talking about our next subject regarding their project, AeroBot. Hélène, Ioannis, hi. I hope you're fantastic. And I want to hand it off to you to present that fantastic project that you have been working on.
Sure, thank you.
Thank you. So hello everyone. Welcome on board AeroBot, so the capstone project of our data scientist training. AeroBot project aims to automatically classify narratives related to abnormal events in the aeronautical sector. And we'd like to thank our mentor, Alban Thuet. And in the absence of our teammate Hichem today, Ioannis and myself will be your flight crew on board AeroBot. So following a quick introduction, we will present our business use case and our data set using our Streamlit-based demo. After discussing our methodology and modeling approaches, we'll use the demo once more to evaluate our model's performance and conclude. So AeroBot's motivation is threefold. First, a business need. In aeronautics, new business models that are based on contracts by the flight hour shift maintenance costs from the airlines to the manufacturers. And predictive maintenance is the key to minimize these costs. Until today, maintenance-related textual data is abundantly available, yet remains mostly unexploited. Second, our desire to experiment the capabilities of NLP in a technical context. And third, the opportunity of open data, as we found the open access online database managed by NASA called the ASRS for Aircraft Safety Reporting System. So this ASRS database contains reports of abnormal events in the US airspace. So these are narratives which are written by the main actors of the event and then reviewed and fully labeled by NASA's experts. So we've then imagined the following fictitious business scenario. So we assume that NASA's costs of maintaining the database are mainly due to the work of the experts who review and classify the narratives. So these are experienced pilots, air traffic controllers, mechanics, each one with a specific domain of expertise. And we assume that they are paid by the hour invested in reading this data. So we imagine ourselves as data scientists at NASA, mission to limit this cost. And our solution is to develop algorithms that will classify the narratives automatically and then transmit them to the relevant experts for final review. Jens?
Don't you see the slide? I've changed.
So I can read it. So we extracted all 108,000 narratives from the last 20 years and focused on 2 columns of the data set. So the narratives shown on the left, which is the input to our algorithm, and on the right, the anomaly labels classify the abnormal event. So the event, for instance, is labeled with 2 out of the 14 possible labels, so deviation, procedural, and ground incursion. And in fact, 60% of our narratives have 2 or more labels, which complicate the task of classification. And today, it will be the task of AeroBot to do the labeling. This means that the labels are the target variable of our machine learning problem. So this is clearly a supervised classification problem where the target feature anomaly has 14 labels. So note that this is not an anomaly detection problem, such as fraud detection, for example, since all the reports describe abnormal events. So each narrative can have several labels. It's a multi-label problem. Therefore, we encode target variable in 2 modes. So 1 versus all encoding, which means 14 different variables being either 0 or 1. So this results in 1 model trained 14 times, so once for each label, and multi-label encoding, where each narrative is assigned a 14-dimensional vector that contains zeros and 1. And here, 1 model is trained at once for all 14 labels. So the latter produces models that are relatively fast to train, but do not allow the use of undersampling. And their versatility across all labels remains to be studied. So in this bar plot, we see how many narratives are tagged with each label. The distribution is clearly unbalanced. So for example, the first label, deviation, discrepancy, procedural, is 30 times more frequent than ground excursion. And this is why we decided to use the F1 score as a performance metric for our models instead of the accuracy, which is not suited to unbalanced data. And to address the scarcity of certain labels, we used undersampling in combination with some bag-of-words models. So this allows us to rebalance the data set. And finally, note that the last label, no specific anomaly occurred, represents a very rare catch-all class that we do not seek to predict due to its variety. And therefore we focus on the 13 labels in the following.
So now let's take a closer look at the narratives. This is our demo, which we set up using Streamlit. On the pre-processing page, we first study a narrative example talking about a weekend trip to the Bahamas. In general, the narratives have an average length of 200 words and are written in formal English without spelling mistakes. In this example, the highlighted text shows us that this pilot mistakenly landed on the taxiway instead of the runway. Notice that taxiways are the roads, so to speak, of an airport that airplanes use on the ground. We can visualize the narrative either in its original form or with annotations and see how many technical terms exist. We have acronyms such as IFR for Instrument Flight Rules and contractions such as FLT for flight. To help the reader understand, we provide a translation of these technical terms. The problem is that we have approximately 500 such abbreviations where both the abbreviated and the expanded form coexist in the narratives, although they carry the same sense. The jargon also contains quantitative information mixed with text. For example, RWY13, which means runway oriented at 130 degrees. Perhaps this reminds you of the kind of textual data in your job, abbreviations of molecules, manuals for handling machines. The approach that we developed in AeroBot can be transposed also to other use cases. Anyways, in order to familiarize yourself with this narrative, we have included a small game for you here that we'll let you try later on your own. Now, with an example, we illustrate the 3 possible forms of text that we may feed our models with. The original form corresponds to the raw full-text narrative and is used for transformer models. The 2 following forms serve bag of words, and word embedding models. The NLP corresponds to the standard natural language processing, that is lowercasing, tokenizing, stop word filtering, and stemming. Our example shows that this does not drastically modify the original narrative. The TLP form corresponds to a technical language processing that is specific to our project and comes on top of the standard natural language pre-processing. In this case, we replace contractions by their full text form. For example, FLT, becomes flight, which is more understandable, and expressions are replaced by their acronyms. Instrument flight rules becomes IFR to avoid counting 3 separate words. And finally, we use regular expressions to separate numbers from textual content.
So now that we have our data pre-processed and our target feature encoded, so what's the flight plan? So we first isolate 90% of our data sets, that is almost 100,000 narratives for the modeling stage. So train models, evaluate them, and select the best one. And our ambition was more to focus on experimenting with various models and their options to evaluate their impact on performance, rather than only racing for the highest scores. So we test 5 modeling approaches, bag of word models, with and without feature selection, down to more sophisticated approaches such as word embedding and transformers. So we train these models using an 80 to 20 train test set split, and considering all the modeling options used, we end up with an arsenal of about 100 models. So the challenge in our project was then to find the appropriate methodology to efficiently compare these models to each other for all the anomaly labels and select the best model. And in the second part of our demo, we will show how we achieved this, introducing the notions of overperformance and versatility of models. And finally, the 10% of data isolated at the beginning are then devoted to error analysis and repeatability checks using the transformer model. And interestingly, we found repeatability issues when using TensorFlow that have also been reported in the cited publication, but we will not dive deeper into this in this matter right now. So we use a decision tree as a baseline model. So we start with NLP pre-processed narratives and use a count vectorizer without feature selection nor undersampling. So this yields a vocabulary of more than 50,000 tokens, which strongly limits the choice of classifiers. So we chose a decision tree because it's a lightweight model with an embedded feature selection. And the target variable here is coded in the 1 versus all mode, so 14 variables to predict. So the graph here shows the F1 scores obtained on the test set. So in general, we observe that the more frequent the anomalies on the top of the graph, the better the decision tree performs, with some exceptions, such as flight deck, cabin, aircraft events, for instance. And these scores will be used as a standard of comparison for the other models. The decision tree of our baseline model has also another advantage, interpretability. So for each token in the vocabulary, it returns its importance for the prediction task. So for example, the aircraft equipment label on the left is characterized by the presence of tokens related to maintenance, inspections, or parts of the aircraft, such as engine. And the flight deck, cabin, aircraft event label on the right relates to tokens such as smell, smoke, odor, fume, or medical vocabulary. So this is also consistent with the standard NLP pre-processing of our narrative. So as you see, some tokens will still appear twice, so in their abbreviated form, and in their full text form, one stem, such as maint and maintain for maintenance, or emer and emerge for emergency. And now you will see how we use token importance to drastically reduce the size of the vocabulary in a supervised way. So after the baseline model, In the second approach of our experiment protocol, still in the bag of words framework, we seek to reduce the size of the vocabulary in an unsupervised way. So here we experiment two ways to vectorize the TLP preprocessed narratives: count vectorizer, which simply counts the word frequency in the narratives, and TF-IDF vectorizer, which also takes into account the specificity of the vocabulary in the corpus. So different vocabulary sizes down to 500 tokens are tested, and this vocabulary size reduction allows us to train more consuming, better performing classifiers such as random forest or naive Bayesian classifiers. In the third approach, still in bag of words, we reduce the size of the vocabulary even more, down to 20 tokens, by selecting the most important tokens as presented in the previous slide, but this time from the TLP preprocessed narrative. And this is why we call this supervised feature selection. Here we can test more demanding classifiers, so random forest, gradient boosting, SVM, and also optimize their hyperparameters. And the vocabulary is supervised for each anomalies, therefore necessarily in one versus all mode, which also enables us to test undersampling. In the fourth approach, we leave the bag of words to represent the words by word embedding. And because the dimension of the vectors representing each word is high, we switch to dense neural networks. The target feature in this approach is coded in both forms, so one versus all and multi-label. And in the fifth approach, we experiment with a transformer model consisting of the 12 embedding layers of a BERT instance and classification layers in the dense neural network. So we confronted two transfer learning approaches, frozen BERT, so keeping all the weights of the pre-trained model, versus unfrozen BERT, where we retrain only the last 4 layers of BERT on our data. And in this approach, the target feature is coded as one multi-label variable. And considering all the modeling options tested, we end up with a total of 100 models.
So now let's go back to our use case. Our online tool helps the aviation experts identify the model with the best performance for their respective domain of expertise. Suppose I am the expert specializing in aircraft events. To easily compare all models, I want to plot the difference of the F1 score with respect to the baseline model. Here, the first line in green. The models that perform better will point to the right. The overperformance of transformer is obvious, is the models down in red. Note that I can see the details of each model in this section, if I wish to. Now I promote myself to the position of administrator of the database. Which modeling approach brings me the highest performance gain across all areas of expertise? As an admin, I prefer multi-label models because they are cheaper to train. Among these models, which is the most versatile one? Versatility means that the model overperforms the baseline model for all labels. In other words, the difference in F1 score compared to the baseline model must be positive for all labels. This graph summarizes the previous bar plots. Each box shows the spread of the F1 score difference across all labels. Graphically speaking, the versatility of a model means that its box plot lies to the right of the vertical line that marks the baseline model. We see that most box plots lie near the black line. Notice how much the frozen transformer underperforms. Now I keep only the best models from each category. Note that the retained word embedding model, here shown in violet, corresponds to its one versus all implementation. I've now grouped the best models in a dedicated plot to better compare them. Model number 93 lies most on the right, so it's the most versatile model. In the last graphs here, we compare the best model to the baseline for each label. The performance leap of the transformer in red is considerable, yet at the expense of interpretability. You can find more resources on our publicly available Streamlit demo, such as a more thorough presentation of our dataset, a focus on interpretability of the baseline model, and detailed key learnings on modeling. Now, we've talked a lot about model performance. Let's talk a bit about cost and effort. We summarize here in a purely qualitative way the effort required to implement each model family against its performance. What we just saw on the demo explains the order on the horizontal axis of performance. The better a model is able to grasp the jargon of the narratives, the better its classification performance. And that's a transition from bag of words to word embedding, and finally to the unfrozen transformer, whereas the frozen version of the transformer shows extremely low performance. The vertical axis shows that word embedding and transformer models require more effort than bag of word models, due to the corresponding libraries, which are more complex to understand and also to implement. These models also are greedier in terms of computing power, especially the transformers. So in conclusion, in AeroBot, we observed that narrative preprocessing does not improve performance when using transformers. The most sophisticated models perform best. And finally, if the sophisticated models of type 4 and 5 are parameterized too simply, performance will suffer badly. We now propose some perspectives to improve the performance. In terms of feature engineering, for our bag of word models, we propose the extension of features by taking into account, for example, bi or trigrams. Also exploiting additional explanatory data that are available in the dataset, such as the time and location, the weather conditions of the event, etc., might help. In terms of modeling, we think that training our transformer model in a one versus all modes would be beneficial because it has been for the word embedding models. This will allow us to apply also undersampling. Besides exploring other large language models, further optimizing key technical aspects of deep learning, such as the classification, head architecture, the optimizer use, etc., can also help. More generally, there are also other perspectives, such as fusion or hybridization of models. In AeroBot, we see that the most complex models perform best. Unfortunately, as they are the least explainable, two methods to address this are integrated gradients for visualizing the model and the word embeddings and study the similarities between sentences in order to develop an intuition on embeddings. So, ladies and gentlemen, we have reached our destination. Thank you for choosing AeroBot for this trip inside TLP.
Thank you very much, Janice and Hélène. Let me now welcome once more our fantastic jury members. That way, they may also challenge your project and maybe offer some perspective from their point of view. Welcome back to our jury members, and let me hand it off to whomever has a question.
Well, first of all, thank you for this work. It's very clear. My first question would be about like this problem in particular. It's probably solved by some humans. Some humans might know how to classify this. Let's call those human experts, like people who know about those kind of texts. What can we learn from them? What can we learn from the expert knowledge to improve feature engineering?
Okay, so I can answer that. So you're completely right. The experts are humans, as mentioned in the description of our use case, and we actually already have used a part of their input in our project because we used the documents that are available on the SRS database to identify the abbreviations and replacing them. So there was some dictionary, so to speak, of the abbreviations. So this is a form of expert knowledge that has flown in. Then we had imagined, for example, to detect other such abbreviations when we would, for example, visualize the bi or trigrams. And then we could submit this for revision to the experts. But we did not dig further into this because it did not serve our transformer model, and we chose to prioritize on that one. But definitely, it would be also in the transformer model case, it would be interesting to replace all the abbreviations by the full text form, because the transformer can actually get the context of words. So this could actually also help the transformer model. And then what I want to say is that there was an issue with granularity of the target data, the labels, the 14 or 13 labels that we mentioned. We noticed, for example, that we have only one category for the label, which is called anomaly aircraft equipment, while we have 3 different labels for problems describing contact with the ground, like ground event, ground incursion, ground excursion. And I think we could use expert knowledge to better define these labels of the target feature.
Thank you. Another question I have would be, we saw many things with different vocabulary size. So obviously there are too many words, so you have to use only a subset, not to overfit. How do you choose the size of the vocabulary you are keeping at the end? How did you decide in the end the size of the vocabulary?
I can answer this question. So as we showed in the presentation, for bag of word model, we really did an extensive study on the vocabulary size with the aim of reducing it to a maximum in order to both reduce the computational cost of modeling and also to improve the performance of model to avoid overfitting. So in this unsupervised vocabulary selection, we noticed that we had to be careful not to reduce too much the vocabulary because we could drop rare words that did not appear in many texts, but that were characteristic of a rare anomaly label. On the other hand, in the supervised vocabulary selection, we have a vocabulary which is specific for each label. We got that from the tokens important from a first decision tree. So depending on the classifier we used, we kept the best compromise between speed and performance for each anomaly label. And for example, this approach was very, very beneficial for random forests, for instance, because of their inner feature selection. On the other hand, in the multi-label approaches of word embedding and transformers, we had to keep a larger vocabulary, up to several thousands, to stay versatile, as we noticed in the unsupervised vocabulary selection.
Thank you. That's all for me.
So hello, Francois here. I wanted to know how you would handle new terms coming to the corpus. Let's say you deployed your model on some material to analyze. How would the model behave with coming across new technical terms or new abbreviations, and would they be ignored or flagged or?
So I can answer that. So when classifying a new report, the model will try to generate an embedding for each token. So I'm referring to the transformer model in this case, and then it will classify it based on the learned representations from the trained data. So if the new terms are not present in the vocabulary of the pre-trained BERT instance, the model will treat them indeed as unknown tokens and generate a default representation for them. So thanks to the retraining of the transformer, the unfrozen model that we mentioned, this model has learned actually some aeronautical jargon, the ones that it saw in the training corpus. And if this jargon came to evolve in the future, for example, if we have a new abbreviation, so then we could either ask an expert to replace it with its explicit form and hope that some words will be already known from the BERT model and it will manage to deal with them. Or in the worst case, we would have to retrain our data with an updated corpus that contains the evolved vocabulary.
So you see your model as a cost cutter. Is that the potential commercially? You said eventually it would reduce the number of analysts or number of experts, and this would be a benefit from using this model. Do you see other practical applications? And
well, I can answer this. So there are two cases. First, when the narratives are written so post-event. So as we shown in our business use case, it can be used to classify the future reports, allowing the relevant experts to quickly review and review them, act upon them, and then understanding the causes of anomalies can help NASA's experts focus on finding preventive solutions, such as new procedures or recommendation to the airport regarding runways, for instance. We could also imagine that if collecting narratives prior to the event, or we can imagine sentence by sentence like a radio transcription during the flight, we could also imagine predictive solutions. So we could imagine a chatbot that would provide live troubleshooting suggestions and help prevent anomalies in real time. And so feeding our chatbot sentence by sentence, we could see how it updates its recommendations step by step, and conversely, how the actors adapt to it in real time. But we have to keep in mind that the current model is trained only on a data set of narratives related to abnormal events, so no narratives of normal events, so it's not an anomaly detection model.
thank you.
Okay, I think it's my turn now. First of all, thank you very much for this presentation. I think your project even grown since last time I saw you talking about it. Very quick question. Usually when we try to put into a production model like this that is going to do the job of experts, we prefer to be careful and to, first of all, use this model as a decision making algorithm and or help the decision of a real human. How do you think your model and your project here can be adapted to a problem of decision-making problem in the fact that they will give insight to the experts to make the decision afterwards?
Yeah, in our business use case, so we are transmitting we were transmitting the narrative to the relevant expert for a final review indeed. So if we wanted to adapt this directly to a decision-making problem, we could, for example, add a decision layer on top of the classifying model. So mapping predicted labels to a set of decisions. So the decision mapping could be designed by a business logic or an expert knowledge. And additionally, we could also take into account the related costs and benefits of the actions. So instead of solely relying on the label accuracy, for example, in our use case, if the NASA's experts have different salaries, so sending reports to a more expensive expert might blow up the costs.
All right. And do you think that it could be possible to use interpretability models to maybe focus on the words that the expert will look at in order to conclude if the classification was well done or not?
Exactly, and this is why we mentioned interpretability of our models to as a track of improvement of our models, and especially thinking that it would help NASA's expert understand the causes of anomalies and act upon them.
Okay, great. Thank you very much. I have a last question. I try to be quick because we're already late. So this project was made of many steps that you followed carefully and that you presented today, which one of those many steps was the most time-consuming, and why? What is?
Yeah, I can comment on that. The first thing that comes to my mind is related to the data set. So in the very beginning of the project, we took considerable time to define the content of the project, and this means that we had to invest some effort to appropriately choose the correct target variable. Because there were several candidates. You can see that on the ACRS database, it's a quite complete one, and there is not only the label anomaly, there are other things like primary problem, etc. And I think this was a very important step because I believe it's also how real life data science problems often work, which means that some customer can come to you and say, look, I have this data, what can I learn from it? I know there's potential, but I'm not sure what I can do with them. And we had that perspective also with AeroBot in the beginning. And then there is another more scientific and technical aspect was related to the pre-processing. So we thought in the beginning a bit with our human way of thinking that pre-processing would be extremely important for the performance of models. So we invested an entire sprint, as we call them. So it means 4 weeks of work in that pre-processing part. And finally, to discover that basically the transformer model, which was the most performant, didn't actually wasn't influenced by the pre-processing. And I want to stress also the fact that there was some effort, more than anticipated, in refactoring the code and delivering actually a code based on on object-oriented programming, which is available on the GitHub. So yeah, to cleaning up this code was actually a long task also that took some time. And perhaps last thing was that AeroBot, I think the main difficulty, let's say scientific-wise, like data science-wise, was that we had 14 labels and also multi-labels, so multi-classification, multi-label problem. And this means that one single metric was not sufficient to classify the performance of the models among them. And I think the main work that we delivered here was all these this proposal of defining a baseline model and then building the differences and analyzing this visually and also numerically, quantitatively, and to be able to classify these 100 models that we had trained, actually.
Great, thank you very much. I was happy to have this answer, because most of the time when we talk about data science, the dream we have that we will spend most of the time on modelization and creating new models, but in reality there are a lot of other things that we have to do that are not as sexy as modelization, like cleaning the data, cleaning the code, preparing the problematic, which is not easy at all also. So I think you during this project you had to follow all those steps, which include modelization, but also all the other things. Thank you.
Absolutely.
Thank you very much, Janice and Hélène. Fantastic project, and so many use cases that we can think about with something, either the concrete model that you set up or something very similar. If I may, now let's just take a few minutes to chat with Francois, who's the last of our remaining jury members that we haven't met into more details. Francois, thank you very much once more for joining our call. Maybe if you can give us a little bit of an insight into who you are, what brought you here, and what you're currently doing.
I was working with GPS at a time, and lost my job eventually because the company went bankrupt. And after a while, I took data scientist, the accelerated courses for becoming a data scientist. And during the boot camp, I really enjoyed all the subject matters that we touched on. And of course, it's great to learn, but it's also much better to put it into action. And then I started a company, a bit like Mark. I'm providing consulting and services to entice companies to use data science if they're not already doing so. I also wrote a book to try to convince people of the benefits of using data science in their company. And I got my first contract in September. This is all new. I started a few months ago, and it's really going well. And just to add on to Alban's comment, you spend 80% of your time pre-processing data in real life, and the modeling part is at the end is 20% of the total work. Is getting very nice data is fun in a context of teaching and learning, but in real life data is all over the place. There's lots of infinities, strings, nans, outliers, and missing values that you have to statistically account for. And the decisions you're making are really have implications, have meaningful consequences in the field you are in. For example, I'm working on a medical device right now that's going to help experts validate their assessment of a patient. And you can't use K-neighbor to fill nans, for example, because if you're using K-neighbor, you're sort of transferring medical characteristics of one patient to another indirectly, and this is probably fine statistically, but medically it's a no-no. It's something you can't do. So those are the constraints that in real world doing real data science project you'll come across. And this is why I accepted to be part of this panel. It's because I really enjoy looking at other applications and looking at fields that I don't know very much. I like to learn new projects and learn new ways of doing or tackling a particular problem. And this is also the advantage of being a self-employed or a small company, is that you're called upon to touch on different problematics that are always in different fields and always as infinite as data science subjects.
No, definitely. Maybe in just a couple words, if you had to convince a company that isn't using AI or data science in its processes right now, what would you say in just a couple words to try to convince them?
You have to build a case study. You have to look at the data that they have access to and what they're doing currently with this data and how this data could be leveraged to increase productivity, to maybe make experts more productive by making some kind of filtering at the top of the raw data. But every case is different. But basically what you're trying to assess is what data is available, what kind of activity is this company doing, and how can data be leveraged to increase productivity, create new products or services, and even help them be more optimized and efficient. But I'd answer it's a case by case situation. There's no general way, but you're trying to prepare a good business case for the company that you have access to. And it's really funny, but there's a study 3 years ago that said that maybe 70% of all European companies do not currently use machine learning or artificial intelligence in their processes. So basically all this data, this company data, is sitting there and it's not being leveraged, it's not being optimized, it's not being used to create new products and new efficient processes. So the potential is really big for data science in the coming years.
Thank you very much, Francois. I think we That's all we have time for, unfortunately. I want to thank everyone that was here today for participating in our DataDays. I also want to thank one person that maybe isn't expected this, but is behind the organization of these DataDays, which is Danny. So thank you very much, Danny. Usually we like to thank the people behind the curtains helping to organize everything here. So thank you very much for your help and assistance in creating this opportunity. And let me invite everyone back on stream for maybe just a quick little goodbye to everyone. Thank you very much for attending. Thank you very much for your efforts, your fantastic projects that you've gone and developed. And thank you to our jury members, which have brought their expertise, their insights, and their knowledge into what it means to be a data scientist, a data analyst, an ML engineer, what it means to work in this profession today. It's really been a pleasure. We're already looking forward to the 7th edition of the DataDays. But thank you, everyone, and I think you all deserve a little round of applause. Thank you very much.
Thank you for the invitation.
Congrats, everyone. It was really a pleasure to work with all of you. I discovered a lot of new things. It was very interesting regarding both of the projects. So thank you again, and thank you to all the viewers, to all the participants who also had some question in the chat. I hope you all have your answers now. You can also, of course, check the Streamlit of those two projects on our studio, so studio.datascientist.com. Make sure to check all the other projects too. They are all very interesting. I hope you had a great moment. You had a pleasant moment, and to see you also to our next events soon. Thank you again.
Thank you very much. Have a fantastic day, and
Bye, guys.
goodbye to everyone.